Okay, we are starting second talk of our today's session with Yevheniia. And okay, welcome, Yevheniia.
Yeah. Hi, everyone. So I have to say sorry, like my voice is not very good today. I managed to get a very rare thing of the flu. Amazing. So let's see how far I can last. Yeah, okay. So, well, today I will tell you about something very unusual for this conference, but I hope it will be very interesting. So the main idea of my talk will be to advertise you a very interesting, realistic problem that lacks understanding on the side of people from conventional community, especially people who specify quantum impurity problems. So, yeah. Okay. Everything that I will tell you about was done together with Jian Tan and Alexei Mikulenko, who are students in Leiden University, Vadim Chianu, co-organizer of this conference, and Alexei Boyarsky, who is a particle physicist. So yeah, as you have seen from the title, this talk is somehow an interplay between condensed matter physics and particle physics. So yeah, again, I will tell you how the problem of quantum impurity became really crucial, central question in an astrophysical experiment, but not just arbitrary astrophysical experiment, a very important one, a fundamental one. So please bear with me. I think it's a very important problem. So yeah, it appears that for certain class of experiments, quantum measurement devices, especially like quantum measurement devices with quantum impurities, play a very important role. Specifically, it's possible, like specifically if we're talking about a so-called Relic neutrino detection experiment, which is able to open a new era in cosmology. This experiment is not possible without full good understanding of the physics that is happening in the quantum measurement device. And the physics is very rich, and there's basically a zoo of conventional effect going on there. And the main issue why people cannot proceed with this experiment is because they don't yet fully understand this physics. So let me tell you why it's so important and why this experiment is so fundamental. You all probably know about so-called cosmic microwave ground. Basically, it's a photograph of a baby universe. Well, not so baby. This photograph shows us the universe when it was like 100,000 years old. And the reason why we can see this universe back in time is because photons, when the universe was very, very hot, photons were interacting with matter. But then, as it was cooling down at some moment, the universe became basically transparent for the photons, so they decoupled from matter. From that moment, which was 100,000 years after Big Bang, photons were propagating basically linearly without interacting with anything. So, and how we measure them now is exactly how they have been back then. Interestingly, with neutrinos, this decoupling appeared much, much earlier, namely after 1 second after Big Bang. And also, well, so we would hope that neutrinos can play the same role as photons and bring us a picture of even earlier universe. 1 second after Big Bang, this sounds amazing, right? There are many photons here in the room, and there are many Relic neutrinos in this room. So naively, we would think that, well, that shouldn't be so hard, right? We just need to measure the same background as from the photons, but from neutrinos. But for some reason, no one have done it yet. So, well, why is it so hard? Why we have not discovered yet the cosmic neutrino background? Well, I think it's important to get some background about the particle physics part of the talk, just that you feel comfortable. So what is neutrinos? Neutrinos are particles that were discovered during beta decay, basically when the atom undergoes a transition that the neutron becomes a proton, like decays into a proton plus electron, plus maybe something else. So if you have a nucleus, this nucleus becomes an ion and emits an electron. So how did people understand that, well, it's not only an electron that is being emitted. If you look at the spectrum, in case if there was nothing else but electron, we would see just a delta peak, right? Because the energy of electron is fixed by conservation law. Also, besides it, we know that, well, both neutron, proton, and electron are fermions. So there's something wrong with the angular momentum conservation here. From both these factors, well, people realized that there should be something more. Well, and the spectrum that was actually measured was not delta peak, but a continuous spectrum. So the emitted electron could have had like different energies, not only fixed one. From this, people made a conclusion that there should be another particle. Pauli called this particle neutron. Well, obviously from charge conservation, right? So the third particle should be neutron. But after the real neutron was discovered, this particle was called neutrino. Also because, well, it's clear, it can be clearly seen that this particle is massless or almost massless. So it's like little neutral particle, neutrino. Okay, so as soon as it was discovered, Pauli realized that, well, it's actually very hard to detect this particle, because if you calculate the cross section, you would see that it's extremely small. It's actually like 25 or 23 orders smaller than the Thomson scattering or just nuclear scattering, where you consider the nucleus to be just a sphere. So, well, how would we detect it? Nevertheless, it was done by Clive Cowan and Frederick Rines. They just decided to solve the problem. Well, if you have a scattering cross section which is very small, let's just take very big amount of beta decayers, right? How we can do it? Well, we need a radioactive material. Let's just go to the nuclear reactor. So they use the huge flux of antineutrinos from the nuclear reactor, compensating small cross sections, and indeed, neutrino was detected. The spectrum of the beta decay can be understood and derived really very easily if you just consider Fermi golden rule with perturbation, which is point-like. This is because typical wavelengths of electron and neutrino are much, much bigger than the nuclear size. That's why on these energy scales, you can consider your nucleus to be point-like. So if you just take this perturbation, like just point-like perturbation with some coupling constant, Fermi coupling constant, you can derive your spectrum, which starts from like the minimal energy of electron, the mass of electron, and there is some maximal energy, which is called Q value, and it is just defined by the mass difference of initial and final particles. Okay, from this, we can conclude that, well, the neutrino is massless, because the maximal energy of electron is within the precision of the experiment is exactly a Q value. In a sense, if you take a Q value and put the mass of neutrino to be 0, that's what you would measure as the maximal energy of electron. Also, we see that this. This Fermi interaction predicts not only the beta decay reaction, but also neutrino capture reaction. You can actually just put your neutrino to the left side. It becomes from antineutrino to neutrino, and you have a reaction where the neutron captures neutrino and decays into proton and electron. This reaction is clearly thresholdless, so even neutrinos with 0 kinetic energy can be captured. And well, if you also think about the fact that the relic neutrinos, so the neutrinos that are coming from all those times and that were penetrating to the whole universe, and the ones that we want to measure, they have very low kinetic energies. Because this energy is defined by the temperature that the universe had back then. Because they have very low kinetic energies, you want a thresholdless reaction to detect them. And that's exactly the neutrino capture. Okay, sounds cool. So, well, but before that, before looking into that reaction, we also need to take into account that the neutrinos are actually massive. This can be, well, this was convincingly observed from so-called neutrino flavor oscillations, but I would not go into the details of that. I just only want to mention that there are basically three kinds of neutrinos, and what people can measure is the difference between square of masses. However, they cannot measure the absolute value of the mass. The absolute value of the mass is still unknown. There's only an upper limit, an upper bound on it, which is roughly the sum should be less than 1 electron volt, which is very low, but not zero. So we have these two reactions, a beta decay and neutrino capture. And if we look at them and think how would their spectra look like in case when the neutrino has non-zero mass, we would understand that the beta decay substitutes like a bulk of the spectrum, it's like a background. And the neutrino capture, if we have relic neutrinos, which are very soft, they have almost zero kinetic energy, this would add a small delta peaks that are separated by the mass of the neutrino from the Q value of the decay, right? So if we observe an electron that was created in the process of neutrino capture, then the energy of this electron is fixed, and this energy will be Q plus mass of the neutrino. So this delta P corresponds to relic neutrino capture. And once again, we have a beta decay background, which is a continuous background because electrons can have different energies because this Q that is released in the decay is distributed between neutrino and electron. However, here also the maximal energy of electron now is not Q, but a bit less, if we account for non-zero mass of neutrino. So already Weinberg in 1962 pointed out that this can be a nice way of detecting these relic neutrinos, namely observing these delta peaks at the end of the beta decay spectrum. And what I want to also point out here that, no, here I don't point out anything else. Okay, so we have these two reactions, and we kind of see a way to detect this CNU B background from these delta peaks. Please note that these pictures are really schematic. Here it's assumed that there is only one neutrino with one mass. In reality, there are three masses and there are three peaks, but this is just details. It doesn't change the quantitative picture. Well, relic neutrinos do leave some signature in the spectrum, so we can measure them. But now the question is how to do it and if it's really technically achievable. So what are the challenges of such an experiment? If we look again at the spectrum, we would see that immediately that first we need extremely high energy precision, right? Because the typical values of Q value of the energy released in the beta decay is kilo electron volts or tens, hundreds of kilo electron volts. And the mass of neutrino is expected to be like tens of milli electron volts. So we want to measure a very small energy gap at the very large energies. So we are looking at energies of hundreds of kilo electron volts, and we want to measure the feature which is separated from that energies by tens of milli electron volts. That sounds very hard. For this, we need very, very high energy precision. But this is not the only problem. We also need sufficient activity rate. Namely, we need to have sufficient number of events per year, a number of relic neutrino capture events. of course, because if we don't have these events, we don't see the peak, obviously. And here I want to note that, again, this picture is very schematic. What in reality happens is that the number of Relic neutrino events is extremely smaller than the number of beta decay events in some energy range, like 1 electron volts, because the neutrino capture corresponds to a fixed energy, and the beta spectrum has it's a continuous spectrum. So even if you take a small energy beam, you would observe much more events than in neutrino capture. That's why it's understandable that the second problem is only a problem, or it's a crucial problem for Relic neutrino detection, but it's not such a crucial problem if one wants to just measure the neutrino mass, which is also a very important, a big problem. And the neutrino mass can be measured if one reaches just high enough energy precision, right? If one will just see that the end of the spectrum is not at Q value, but a bit less. And this difference would determine the mass of neutrino. So these are two challenges. Now let's think about how would the experiment look like that wants to achieve this goal. Yes? T is just the kinetic energy of electron. Electron, emitted electron. Okay, so first of all, well, as we said, we need high enough activity. For this, well, it has been shown that we have to take emitters with low Q value. So, okay. Well, again, as I said, you can look up in the literature that the cross section of the neutrino capture decays as 1 over Q cubed. So we already have some glimpse on which emitters we can take and which we cannot take. Then,
what is Q value?
Yes.
What is Q value?
Oh, Q value is energy released in beta decay. Basically, it's the difference of final mass, initial mass, the mass of the initial nucleus, and sum of the masses of final nucleus and electron.
Yeah, thanks.
The mass difference. How do you call it? Yeah. Defect. Okay, now we need a high number of emitters because we need to have at least 1 event per year, or 2 or 3. And actually, if you calculate, if you do physics, if you do calculation, you would see that you need to have 10 to the power of 25 number of your atoms, radioactive atoms, which is a huge amount. And now you will understand why this amount is actually so hard to reach. One more detail is the lifetime of emitter. Well, it shouldn't be too large, because then the lifetime is basically, if the lifetime is infinite, your emitter is stable. You don't have any events. So you want this lifetime to be not too large, but you also don't want it to be too small, because, well, you would not manage to make your experiment, because your material would decay before you do it. And now from the other side, we want high energy precision. For this, we also need low values of low Q values, because we want to measure a small feature at high energies. So the smaller the energies, the easier it is to distinguish this feature on them. We also want to have low emitter densities. So imagine you take some, well, obviously, if you take your radioactive material in a solid state form, well, you're screwed, because your electrons will just scatter on the crystal. So imagine you take your radioactive media in the gaseous form. Well, then you have a requirement that the free pass of the electron should be bigger than the system size of the experiment, because the electron at least shouldn't scatter on other emitters. Because then what would you measure doesn't tell you anything. And from this simple requirement, which is a very, very rough requirement, actually, there are much bigger problems. For example, when the atom decays, it becomes ionized, right? So electron would also scatter on the ionized or on the charged centers. And the scattering cross-section for such a process is much bigger. But even if we look on a simple scattering on just spheres, of other emitters, we would see that the size of the linear size of the experiment should be 1 kilometer. And then you take volume and you see that you cannot really reach it. And even this is not realistic because if you take a gaseous form of some atom, for example, people usually take tritium due to the fact that it has low enough Q value, nice lifetimes, and people know how to deal with tritium. So if you take tritium, it tends to form molecules. And you will see later in my talk that if your atom is in a bounded state and the molecule is a bounded state, not all events would be you would be able to distinguish not all the events, and the ratio of events that you will be able to distinguish in case of molecular tritium is extremely low. So this naive estimate of 1 kilometer gets much bigger. So, well, here I just want to tell you that, well, the gaseous tritium, the gaseous form of atomic emitters will not work for sure. One more thing that is, you have to have low volume because, well, here I don't want to go into details, but there are collimation procedures which restrict your volume, which put the upper threshold on the volume. So, well, you want to have low emitter densities, low volume, but high number of emitters. You cannot reach it with a gaseous form. These three criteria, they just don't work together. And from this, you basically conclude that the only possible way to construct such an experiment, which has an extremely important goal, is to use a solid state based experiment. Basically, when you can attach your emitters to some solid state substrate in some regular manner, and you can achieve high densities of this emitter, and you wouldn't have problems which you had before. So, well, okay. So we make a conclusion that the only way out is to use a solid state based experiment. And that's what was done. So the Ptolemy is a collaboration which has a state-of-the-art Relic neutrino detection experiment. It's a very big collaboration. They are founded by Simons Foundation. There are many people from Princeton, Amsterdam, Milan, Rome, and they are working really hard to achieve this goal. And what they managed to do is they managed to build a measurement apparatus that has extremely good energy resolution of 10 milli-electron volts. And if you remember the estimates of neutrino mass, well, 10 milli-electron volts should be enough, should be good. But, we will see that it's not, well, okay. And if we look at their promises, you can remember my schematic pictures from the beginning. Here, the red is the background of beta decay, and the green is delta peaks from neutrino capture. Here you see two delta peaks because, well, as I said, there are not only one mass, but more masses of neutrinos, mass eigenstates. And here you see the dashed point. The dashed line is how would spectrum look like if you had a perfect experiment with perfect energy resolution. And here you see that it's the delta peaks from Relic neutrino capture, for example, is a bit smeared. It's not delta peak anymore, but it's some Lorentzian or whatever peak, smeared peak. But it's not very smeared. It's still distinguishable. It's just not that crucial. So it looks really hopeful. It looks like we can do everything. Well, also please keep in mind that this is a logarithmic plot. So, well, you really have much less number of neutrino capture events than the background, much less. So, well, is it? We can do everything? Well, the answer is no. The answer is that, well, this huge Ptolemy collaboration, which was working so hard for this huge and important goal, cannot yet do it. And the reason why they cannot do it is very fundamental, crucial, and it lies in the solid state part of the experiment. So the reason is that the width of the peak, namely the uncertainty of the energy with which you measure, of the electron that you measure, is not only determined by the energy resolution of the measurement device, which is very good for Ptolemy, but also by physical smearing of energies of each electron due to interaction with environment. Well, before your electron comes to the measurement area, to the measurement device, before it comes there, it would interact with the substrate, with environment, and its energy will change. So this is what we call intrinsic smearing. And then the question is, how big is it? Is it also like 10 millielectron volts, maybe bigger? So yeah, we have to really look into that. And then we have to ask ourselves, will this spectra still look like this? Will we still be able to at least somehow distinguish these small peaks at the end of the spectrum? And I have to say that there are many mechanisms that contribute to this interaction, to this intrinsic energy smearing. And these are all mechanisms going on in the condensed matter system, which is your substrate to which you attach your emitters. I forgot to say that Ptolemy used graphene as a substrate for obvious reasons, because, well, firstly, graphene is a two-dimensional material, and if you take something else, you would have very hard times making your surface perfectly flat, right? And if your emitters are not regular, are not situated, are irregular, are basically attached to an irregular surface, you have much bigger problems. So, well, they were working with graphene, and there you have a bunch of effects going on that contribute to this energy uncertainty. In this talk, I will touch only a couple of them, but there are like many more, and that's actually a reason why I'm giving this talk, because we're saying that there are like a lot of interesting physics going on. This physics arise when you look at such small energy scales, and this physics is not only interesting, but also it lies between, like, it just lies on the way to a great goal of CNUB detection. So if you look at the very naive effect that have basically never been important for any condensed matter experiment or condensed matter effect, you would see that it is crucial here, already this. So what is it? Because your emitter is bounded to a substrate, it means that it's localized to some finite area in space. And if you localize something to a finite area in space, you have a Heisenberg uncertainty principle, which means that the velocity of this object will have some uncertainty. Well, okay, the beta decay is happening in the center of mass of the atom. So if the center of mass of the atom has uncertainty in velocity, well, same uncertainty will have an emitted electron, which you will measure in the laboratory frame of reference. So this uncertainty can be really very naively estimated. And you see that this uncertainty is basically defined by, well, the energy of electron itself, the mass of the nucleus, and also the spread of the ground state of the nucleus, basically the oscillator wavelengths. So basically, how well can you localize your nucleus? How stiff is your potential in which you localize the nucleus? Here, as I said, because you have a heavy nucleus, if you want to localize it, it just sits in harmonic potential, which is characterized by stiffness. So you can see how this energy uncertainty depends on the stiffness of the potential. And you see that the dependence is very weak. Basically, if you want to change your energy uncertainty by 1 order of magnitude, you need to change the stiffness of the potential by 4 orders of magnitude, which means that basically whenever you couple your emitter to a substrate, it doesn't really matter how you do it, you would basically have the uncertainty of the same order. So we're not interested for now in this. What we see is that another factor that determines this uncertainty is the nucleus itself, namely the Q value, or the energy released in beta decay, and the mass of the nucleus. And if you just take the values that are used for Ptolemy experiment for tritium, the mass of the tritium is the Q value of the tritium, you will see that this uncertainty is 0.5 orders of 0.5 electron volt, which is like it's surprisingly big compared to the energy resolution that they were trying to achieve with their measurement devices. And this, this uncertainty is 2 orders of magnitude bigger than the mass of the neutrino. So, well, already we are screwed. We are screwed. We cannot detect anything. So, well, this sounds like something that one should take into account in such an important experiment. But is it really so deadly? We see that this uncertainty indeed strongly depends on the nucleus itself. Well, right here you see how does the spectrum changes if you account not only for the finite energy resolution of the detection apparatus, but also to this intrinsic energy resolution. And you see that the neutrino capture peaks are just buried below the beta decay background. We cannot see anything. So is it like that's it? Well, we see that this uncertainty strongly depends on the nucleus itself. So maybe we can find a substitution for tritium that would work better. We have done some studies and we found that indeed there are such isotopes as, well, the best is thulium, and it gives an energy uncertainty that is orders of magnitude smaller than for tritium. And you see on this plot on the right, you see this this is just so you see that in the lower right corner you have more than 4 visible events per year. On the upper part you have basically no events per year, and in between there's something in between. And you see that if, for example, if you look at the neutrino masses of 50 millielectron volts, you can still detect such neutrino with thulium, while you cannot detect with tritium. You cannot detect anything with tritium. Well, it has 500 millielectron volts and energy uncertainty, so you cannot detect anything less than that. Well, okay, that's already a big step. We found an emitter that can work to overcome this silly, stupid school problem that we have found. Is that it? No, that's not it. That's only the beginning. We have still a bunch of other problems to deal with. Let me comment very briefly on them. I'm looking at time, 15 minutes, okay. There is charge screening, right? Because you had your emitter, which was tritium, which was a natural emitter attached to graphene. After beta decay, this tritium becomes a helium ion. So you have an impurity, like ionized charged impurity created at some moment of time near the graphene sheet. Obviously, the graphene would start to polarize, start to react to this impurity, and screen it. When we calculate the spectrum, we account for the Coulomb interaction between electron and the helium ion. If you take it in the vacuum, there is a helium ion, there is electron which flies away. You know the interaction between them. You can calculate the perfectly the spectrum, which you will observe. However, here, when there is a graphene which screens the potential of the helium ion, well, the interaction between this screened ion with electron will be different. Hence, it will also change the spectrum. We can make very, very simple dimensionful analysis and see that the only 2-dimensional quantities here are the distance to the tritium ion and the Fermi velocity in graphene. So we can calculate the relaxation time of graphene, which is 0.3 femtoseconds. And from this relaxation time, we can calculate how far our electron will fly away. And we will see that depending on the energy of electron, it will fly away on something like hundreds of angstroms, which is not that far. And if we consider that during this time, the ion or the helium ion will be completely screened, we can calculate the energy shift as compared to the case when we have unscreened bare helium ion. And we will see that this energy shift is first energy dependent, so it depends on the energy of electron. And this is very important because it means that different parts of the spectrum will feel different shifts. So it's nonlinear. It means that the spectrum will not just shift, but deform in some way. And we also see that it's not small, it's significant. It's of orders of 50 millielectron volts. if we do something more than this dimensional analysis, if we just do quasi-classics and consider just quasi-classical screening of impurity in graphene, we would see, that indeed, here I call it the work performed by electron, but it's the same as the energy shift of the electron, because, well, basically the electron that flies away, if there is a non-zero charge density in the graphene, it would perform work on the electron, right? So it would change its energy and change its spectrum. We will see that this work has indeed order of 0.5 electron volts, and is, well, it's almost linear near the edge of the spectrum. And we are interested in energies near the edge of the spectrum because that's where we have our neutrino capture delta peaks. So, okay, from one hand, this effect is very big because it's of order of 500 million electron volts. Again, from the other hand, this effect is almost linear, which means that the part of the spectrum which we're interested in will be just shifted, not really deformed, but shifted in a linear way. So from one hand, we are not scared of that. From the other hand, the fact that this quasi-classical effect is such strong means that the quantum fluctuations, basically the second moment, right? We calculated the average. Now we want to calculate the fluctuations. If the average is big, we are kind of afraid that the fluctuations may be also big. And the quantum fluctuations will be something we cannot back engineer. If this we can back engineer, well, we see how the spectrum is shifted, we shift it back. Then quantum fluctuations we will not be able to back engineer. This is something that is, well, we're working on now. One more problem that I want to talk about here is the X-ray edge singularity problem, which you are all probably very familiar with. And it basically means that, well, before, when we were calculating the spectrum, we were, well, using a Fermi-Golden rule for the system that consisted from the atom, electron, and neutrino. But now we want to also take into account the graphene, because, well, when during the beta decay, there can be an energy transfer between the emitted electron and graphene, or in other words, graphene can correct the energy balance, energy conservation in the problem. It can take some energy, well, yes. So if you just naively consider the same Fermi-Golden rule with just Fermi interaction, but you include the graphene into it, you would find that the spectrum is corrected by so-called X-ray edge. So if you will calculate the same decay spectrum, right, as we did before, you would see that in this case, when you also want to account for the graphene, it changes. So the smeared spectrum is a convolution between the bare spectrum and the spectral density function of graphene. Okay, let's find, so what we need to find is the spectral density function of graphene. And in this case, well, because we have a problem where there is an ion, the charged impurity created, that's why it's very similar to this X-ray edge problem, and the spectral density would have the same shape. And this shape is controlled by two parameters. One is basically the cutoff energy is defined by the distance between the graphene sheet and the ion, and another is controlled by the electric permittivity of the substrate of the graphene. So if we look at how does the spectrum change in this case, we will see, okay, there's indeed some smearing. It's not as deadly as it was for simple Heisenberg uncertainty problem, but it's still there. And we can also see that, well, this problem can be also mitigated by changing the electric permittivity of the substrate and the distance between the substrate and beta emitter. Okay, well, this study is also still not full, and well, maybe I was too fast. Okay. So, well, what I wanted to show you, let's go back here, is that there are many problems appearing when you want to detect relic neutrinos. Detecting of relic neutrinos is very important. It would just, if people can obtain CNUV picture, it's a complete breakthrough in the cosmology. So this experiment should be thought of on the same level with CERN experiments, and so it's very fundamental experiment. And what we see is that basically the question whether we can actually do this fundamental experiment or not is defined by the question whether we can solve these problems, which are actually just condensed matter problems. And well, what we have found is that the people in particle physics and cosmology community have not thought about them before. And well, by considering a very simple problems from this list, we found that they have to be considered. So this, if you want, is another advertisement of these open problems for you. So you're really welcome to participate and use your knowledges to help reach this fundamental goal. One more thing that I want to say is that it's also very interesting because this experiment allows, well, it has a very long time scales, right? Because we have very small number of events. So it allows to look at the energy and time scales that are usually not accessible in condensed matter experiments. So maybe it can also allow to see some interesting features and phenomena in the same X-ray singularity problem and others that cannot be seen on conventional condensed matter experiments. So, well, as I said, I wanted to basically pose questions, but not give answers to them. And I hope that some of you maybe will be interested in answering these questions. Thank you. That's it. That's it. Yeah.
Just out of curiosity, some prototype has already been built. Thank you, Misha. It's not a particularly clever question. So out of curiosity, some prototype of the device has already been built, or at this stage is just theoretical studies?
Prototypes that would account to these effects. There's no prototype. Yeah, sure.
Yeah. So
yeah. Okay. Well. Okay.
yeah. So the electromagnetic guidance system and the calorimetry module exist. Yes.
Yeah. The part with the extremely good measurement device exists.
Yeah. The solid state part has not been implemented, but the rest of the apparatus have been implemented.
No, I think a part. I mean, some small prototypes were implemented. It's just to go. I mean, for all these problems to become very important, you need really to be at the end, right? You need to achieve already super good energy resolution and so on, and this, of course, was not done yet.
But then you cool down also the solid state device.
You probably need to cool down. Actually, well, right? Yeah, that's a good question. It's the temperature scale, especially for heavy atoms. You don't have to worry about the. Yeah, but well, for graphene to stabilize it, yeah, you probably need to cool it down. Yes.
If you talk about experiments.
Yeah, sure.
I think you need to stabilize the temperature, very good and low temperature.
Yeah, you don't need to go below nitrogen actually. So it's
In this list of hurdles you presented, I mean, are they presented on the order of magnitude of the uncertainty?
Well, you never know the magnitude of uncertainty until you calculate it, right? So we for sure know that the first one is the most crucial one and the most simple one.
Yes.
We also know that the second and the third, well, the second, we still haven't calculated the fluctuations, so we don't know. As regarding to the third, you have seen, it's less crucial than the first one, but it's still pretty bad. As regarding the others, you have to just, I mean, we haven't calculated them. This is a very fresh, basically initiative or project. So we are only starting, and actually after we started working on that, the Ptolemy collaboration were really, let's say, the response was very strong. So they created the plenary meetings and they started to work on it and they started to.
first they ignored us and they laughed at us.
Yeah, right. Okay.
And now they are scared.
Yeah. So I think, well, from what we see, each of these problems can be tackled one by one. Well, we have tackled the first one, and it was the biggest one. It's supposedly the biggest one and the scariest one. So we are hopeful that we can tackle each of them, but it should be done with a big group of theorists. And well, if you actually just carefully approach each of these problems, there is a big hope that we can actually build this experiment, and it's not as an expensive experiment as a CERN or something. So it's, so I understand it in terms of money, it's not.
No. If you start doing it full scale with all this 10 to the 25 or even 10 to the 26, if it is too low number of meters, I mean, it's really something huge. I don't know, it's difficult to say, but it's whether it's more or less expensive than LHC, but it's comparable scale. It's just the science goal is also comparable because you know, to have another CMB, you don't have too many alternatives. It's really very, very, very important goal. So if one can prove that this can be done, I don't think that money is a major issue here.
Yeah, it's also not a purely theoretical effort that is needed here, because we understand some things which happen. So the basic question is how an atom decays, beta decays on the surface of graphene or another conducting substrate. And there are things that we can understand theoretically, but there is stuff which needs to be done experimentally before the whole apparatus is built. We need to know stuff. We need to know effects which are happening there. Surely we listed some effects, but we don't have the slightest knowledge of what happens at that extremely small energy scale. Small energy scales are tricky. So yeah, it's a big effort that we made here. Yeah, but the money is not an issue.
Can I ask a question, please?
Yeah.
Maybe I missed. Is there any angular resolution planned?
Once again, any angular what?
Is there going to be any angular resolution for this neutrino, relic neutrino background in the experiment?
Well, okay, yes. So what people usually do, both in, so there were two experiments so far. Katrine, which is gaseous. They use gaseous phase of atomic matter, and Ptolemy, right, which use solid state base. In both of these experiments, the electrons, the emitted electrons, are post-processed. So they are, with the help of magnetic and electric field, they're all aligned such that they move parallel to some axis. And this is done in a controllable way. And for example, here I showed the estimate for the energy resolution that results precisely from this need to align electrons parallel to one line for gaseous, for Catherine. So you see that there is a source part of experiment and there is a detector part of experiment. The source part of experiment is where you have tritium, gas with tritium, and their electrons are emitted how you want, different angles. And then there is a detector which has a magnetic field, which rotates electrons, and has filter, which filters electrons with energies lower than Q.
Zhenya, the question was probably about angular resolution towards relic neutrinos, not towards emitted electrons.
Right, you see, right.
Yeah. Then the answer is I've seen papers discussing angular resolution, so people definitely think about it. Although I should be honest, I don't understand how this works, but I as it is not clear, I mean, I think we have to understand first that it is possible at all.
Yeah,
so,
sure.
So I didn't think about it, but the fact is that I've seen a couple of papers where signed also by the spokesman of the Ptolemy collaboration when they discuss angular resolution. Yeah.
Okay, so if I'm allowed to have a second question, there are, as far as I understand, there are various scenarios about neutrino masses. So they can be either close to, say, 0.3 electron volts, or the lightest neutrino might be massless, even massless, and then two other species have masses of around, correct me if I'm wrong, around milli-electron volts or tenths of milli-electron volts. I mean, do you assume, so will the experiment, does the experiment have a chance to work in the pessimistic scenario of light neutrinos?
Well, if the energy of neutrino, if there is a neutrino with zero energy, you would still be able to observe the second lightest neutrino, right? Because then, the beta decay part would not be shifted. So you would be able to have an electrons with energies up to Q, because yeah, if we emit electron and neutrino with zero mass, we would have exactly the case with massless neutrino. But if you capture neutrino, you would have delta peaks at zero, at Q, but then you would have other delta peaks that are separated from that end. So you would still be able to detect. In principle, yes, the answer is yes. So you would still, the pictures will be different. You would have a background that goes to Q, and then two more peaks that you would be detected.
Yeah, I would like to add, I agree with Zhenya. I would like to only add that, just a comment, you emit electron, right? So in principle, you are sensitive to electron neutrino. However, electron neutrino is a superposition of three mass eigenstates, right? So that is why all three mass eigenstates contribute, even if you interact, even if your interaction projects on electron flavor. So you do see these three eigenstates, and yeah, as Zhenya said, of course, it's much better if for this experiment, if the lowest mass eigenstate is non-zero, then it's easier. However, the difference is not that huge. If you are already there, that this experiment can work at this scale of energy resolution at all, then the difference between exactly zero and a little bit non-zero lowest mass eigenstate is important, but not critically important. And
yeah,
the last comment is that I wouldn't call this scenario unfortunate. My favorite model, neutrino minimal extension of the standard model, does predict that the lowest mass eigenstate is exactly 0. And many people spent decades of work to advocate this scenario, including myself. So I wouldn't call this scenario unfortunate.
I would want to also add one thing. As far as I understand, well, the Katrina experiment, the gaseous experiment, which doesn't have enough number of events, it still is able to solve the beta part of the spectrum. And as far as I understand, well, there are works which analyze the shape of this end in different cases for different scenarios. So to measure the shape of the end is easier in a sense because you have much more events there. So to judge about the mass of neutrinos, you don't really need to, as far as I understand, maybe Relic can correct me, you don't really need to measure these delta small peaks from capture. You just need to have good enough resolution for the beta spectrum.
Thank you.
By the way, the statistics in this experiment to detect relic neutrinos should be so huge that, first of all, as Zhenya said, before measuring relic neutrinos, much before that, with lower number of events, you will have the best measurement of neutrino mass itself, because the number of events there is much larger. So there is a chance that this will be the first direct measurement of the absolute scale of neutrino mass, especially in these scenarios that you call unfortunate, which I call fortunate. And also, yet another potential discovery is that in this unfortunate scenario, dark matter can be made of keV mass right-handed neutrinos. If dark matter is made of keV mass right-handed neutrinos, then you predict 0 mass eigenstate, 0 lightest mass eigenstate. And then from time to time, you will emit this keV sterile neutrino instead of the ordinary one. And this produces a kink in the beta decay spectrum, which with this number of events and this precision of experiment is also observable. So if this experiment works and the unfortunate scenario is realized, you measure neutrino mass, you detect relic neutrinos, and you also detect the dark matter particles.
Any other question from? I don't see much of online people, but still. Okay. In such a case, we stop recording. Thank you, Zhenya.